So assembly design Workbench has several toolbars. These four are the most important ones for constrain, for move, for manipulation, and the product structure toolbar. So we're going to learn about them. Now, the important thing in any assembly is the notion of constraints. Okay, so what is constraint and what is degrees of freedom? So if you know, when you have an object that is free to move in the 3D space, it has 6 degrees of freedom. From the 6 degrees of freedom, 3 of them are called translation, where an object can move along 3 axes perpendicular to each other, like X, Y, and Z. And in translation, the orientation of the object does not change. Okay, so if I just show you over here from this hex bolt that we had, so here this object bolt, it can move along z-axis without changing its orientation. It can move along x-axis without changing orientation, and the same thing for y. These 3 motions are called translation. So it has these 3, and then it can rotate about the same 3 axes. Okay, so it can rotate about z, it can rotate about y, and it can rotate about x. Okay, so as I said, each object in 3D has 6 degrees of freedom, 6 independent ways of moving. Now, if by attaching it to something else or by bringing it into contact with something else, you take away some of these degrees of freedom, then we call those things constraint. We say the motion of this object is constraint. Okay, so like what? For example, here, let's say if I force this object to stay on the XY plane and never leave the XY plane, we call that planar constraint, right? Then all it can do is to move along X, move along Y, and to rotate about Z. Okay, so out of 6 degrees of freedom, 3 of them are gone. So we say the planar motion or planar constraint will take away 3 degrees of freedom. It's a constraint. Now in CATIA, when we basically put 2 objects together to have contact or any kind of constraint together, we say we create a mate. Okay, so mate is what's the technical term that we use in CATIA. And there are a few different types of mates in CATIA that you can see, and we're going to go over them. But just wanted you to know about the notion of constraint. Or for example, if you have a door, the classroom door has 6 degrees of freedom, but once you put it on the hinge, okay, then all it can do is a simple rotation about the hinge axis. So we say the hinge, out of 6 degrees of freedom, will take away or constrain 5 of them, and then only leaves 1. So that is the notion of constraint, which I hope you have seen in your dynamics course or statics. Okay, so now how do we do such thing in CATIA? So let's do that through doing an example. So what we want to do, we can either go and create this 4-bar linkage, or we can do the universal joint assembly. So if we go on Canvas under modules and go down under CAD files, okay, actually we have to go down under tutorial, I assume. Then we can either get the universal joint files, lower U joint, upper U joint, mounting, swivel, and so on. Or if we can basically get the links for the 4-bar linkage, which I don't see them here. I should have them somewhere, but I don't see them. But what we can do is we can create them actually. Okay, so let me go through that. How about that? So we'll do the universal join later. So what I want is, I want to create this mechanism called the 4-bar linkage, which are 4 links connected together. One of them we fix to be like the ground, and the 3 others are free to move. So one of them is the input link, okay, and the other one is the output link, and the green one is the connector link. So you might wonder, where would you see such a thing in real life? Where is this mechanism, which has 1 degree of freedom overall, the whole mechanism? Where would you see that? Well, in the past, one of the places was the windshield wipers. So one of the wipers was connected to the motor, and then through a small link, it could also move the second wiper. I don't think they do that anymore, but one of the obvious places is in the train. So in order to transfer the motion, the rotation of the wheels from the wagon, right, from the locomotion, the front wagon, to all the ones behind it, in order to move those rotary motion of the wheels, what you do is use this 4-bar linkage. So you say 4-bar linkage train. Let's see if we can see a simple picture of it. So that's what it is here, basically. If you can see, let me see if I can get a better picture of that, maybe. Yeah, I don't know if you can see this here. Okay, or so this is a simplified version of it, this picture. So here we can consider this mid member here, this mid plate, to be the ground. And then the distance between the center to this pivot is like one of the links. This is the connecting link, and this is the output link. So once this guy rotates through this member, it transfers the motion to the other wheel, and they rotate together. So you can see clearly a 4-bar linkage there, and you can see it in other places too. For example, you can see it in us when we are biking. So if you consider the thigh muscle, and then the rest of the leg shank all the way to the feet, and then going back to the center of the sprocket, and then a fixed distance between the hip and the center of the sprocket. So this is basically the fixed link, and then what you do, you start the motion from the thigh, so this member rotates, and then through your legs you would transfer that to the pedal, and you do the pedaling. So you clearly see that guy here in pedaling. You can see it in other places too, like basically the oil extraction mechanisms, oil well. What you can see is another 4-bar linkage, if you can see. And you can see it in other places too, okay? For example, in the lift truck or other mechanism, you can see again, you can consider this to be the fixed link, and then you provide motion at one of the links, and then this is the other link, and then what you do is really through the middle link here, through the connecting rod. So this guy is there in so many real life applications, and now we want to create such a thing, okay? So we want to do that. We need 4 members. All of them are similar in shape. The only thing is the length of them are different. Now the length of them you cannot just choose arbitrarily, so you need to make sure the length of each one is less than the other 3 when added together, okay? Otherwise you would never form a 4-bar mechanism. And then depending on whether some of the input-output link is less than the fixed and the middle link, or it's bigger than that or equal to that, then there are different types of motions that you can create. So let's go ahead here and create a few members, and then we can change and we can see the effect of that. So first we go to new, and we create a new part. Okay, and we can go very fast. So here we go. And what we do here, if you remember, we can use the elongated hole here. That's the perfect tool to create this kind of member. And I turn snap to point on. So I make the first member center to center to be 60 units like that. Then I would create some center holes. So that is too many. If I make this guy 10, that should do it. And then another one, 10. Okay, and then I get out. There we go. And now I would extrude this for 10 units. And that is my first member. And if I want, I remember I can change the color of it, correct? By going through Properties, Graphics, and give it any color that I want. So I will save this as the input member. So I would call it the input link, right? Then I go ahead and change this and save it as a different thing. So this time I go ahead and change this 60 maybe to for example 100 and let's say 100, right? And I get out and I can change the color again, and this guy I can call, for example, the conrod or the connecting member. So I save it as the connecting link. Then I go back here and change this to maybe 80, and I get out and again change the color, save it with a different name. So you see how fast I can create members if I want to, right? Let's see, it seems like I didn't apply it. Okay. Oh, there is something going on here. So this is the connecting link, this is red, this is the input link, yellow. And we can change the color of that. There we go, file, save as, and call this the output link. Okay, and then I can go ahead and change this to, so now I have 60, 180. One small thing I have to do is the output link should be longer, because if I go like 170 here, this like I do 120 maybe. Save. And finally, I would change that to maybe 140 and apply a different color, and I would call that the ground link. Okay, so now I have made all the 4 members. Now it is time to go ahead and assemble it, put it together. So the first thing is, how do I bring the members in to the various assembly? How do I import the members in the assembly? So what I do is, remember, if you want to assemble, you should not go ahead and open the members. So first you go to Start, Mechanical Design and Assembly Design. Then, as I said, in order to bring those 4 members here, you are not going to go to File and Open. You're not going to do that. What you would do, use this toolbar here, which is for assembly, and then you click on this 4th command from the top. It says existing component. You click on that, and when you do, nothing happens until you click on this product 1. When you click on that, then it gives you a browse window, and that's where you can bring in your members. Okay, so let's say you bring in the ground link, right? Then you can repeat the same procedure and bring in the input link if you want. Now here, if it asks you to change the name, you do it. Now you see it put it right on the top of this. So the yellow member is on the top of the green. If you want, before you bring in the next member, you can move these guys around so that they are not all brought in on the top of each other. And in order to move components or rotate them, you bring in the move toolbar, and then you click on the manipulation tool, the top one. And here, this guy allows you to move any component in any direction, or rotate them about any axis, or move them on any plane, or an arbitrary axis or plane. So let's say here, I want to move this guy about along the x-axis, so I click and bring it in the x, and I want to move this guy in the y direction. Then I bring in the other 2 members, so the Conrad I bring in. Again, if I ask you for changing the name, you can allow it to happen. And then here, maybe this one is opposite x. And finally, you bring in the last member, which is the output link. Okay, so now we got all 4 members in. Now it is time to put them together. So the first thing was to bring the members in and to manipulate them so that they are not all on the top of each other. Now it is time to go and apply constraints, which is through the Constraint toolbar. Let me move some of them out of the way so that I can see better. So we go back to our lecture. As I said, there are several main constraints, and I'll try to show you these guys, and then the rest of them we practice in class. So maybe in class we can do universal joint assembly. But the first thing we want to do is, when we want to put this guy together, the first thing is the red member has to be fixed, right? It's supposed to be ground. It should not move. So the first thing we do, in this case, the green is the ground member. So we have to fix it. In order to fix it, we use this anchor tool, which is called fix component. So we click on it, we click on the member, and now it is fixed. By the way, how do I know it is fixed? If I go under the tree, there is now a new tab added called Constrain, and if I expand it, any constraint that I have created is listed here. So I can access them, I can double click on them and modify them, and so on and so forth. Okay, so you see this member is fixed at that XYZ position and at those angles. So I can fix it, but I can rotate it and fix it if I want. So I can change the angle of this member by changing like rotation X to 30 degrees, 90 degrees, 100 degrees or so, or Z, or move its Y. And so, for example, let's move the Y a little bit. Let's just do it at 20 mil. Okay, and then update. So whenever you apply any constraint, that's another thing that I mentioned here in one of the slides. whenever you apply any constraint, as it says here, you need to click on update for that constraint to be physically applied. So here I say, yeah, I want this member to be fixed, but at the location that I tell. That's one thing. The second thing is, okay, how do I know, as I said, is fixed? One is by looking at this, which is applied to it, or this anchor that appears on it, or I can check with the manipulation tool, right? I try to move this member and see whether it moves or not. If it doesn't move, then it means I'm good to go. So here, let's grab it and move it. Ah, it is moving. It is moving along X, it is moving along Z. How come? I just said this guy is fixed, and apparently it is. From this sign or that constraint, I can tell it is. But look, I can even rotate this guy about Z-axis if I want to. Look at that. So it seems like really it wasn't applied. But yes, it is. So first, to get this back to where it was, you can do Control-Z, but the better thing to do is, if there is a constraint, in order to reapply it, if somebody like me came and messed with it, click on Update. It goes back to wherever it was. So why could I move it or rotate it? If you know here, there is this check mark that we didn't check. So it says, hey, drag or rotate, but do you want to do it with respect to constraint or don't care about the constraint, just do it? So if you don't check this, it will move that member or rotate that member as if there is no constraint on it. But if you want to consider whatever we have applied, and then with respect to those move the member, so you always what? Check this. So my suggestion is always check this, so that all of those constraints you have applied are effective. Now let's see if we can move it. Of course not. Okay, so always turn this guy on with respect to constraint. Good. So I got this member fixed. Perfect. Now what? Now the next thing I need to do is to bring this yellow member, the input, and then first put the back face of this yellow member with the front face of the red member, put them on the top of each other, and then make sure that this hole on the yellow member and the same hole on the red member are concentric, right? So this is what I do. I go ahead and use the top constraint called coincidence and say I want coincident this plane, then I rotate and say what? This guy here, right? This front face. So now I want them coincident. Now when you do coincident, there are two conditions for coincident. Either you want the normal vector to those planes to be the same, or you want them to be opposite. When you say opposite, means what? Means one of the normal vectors is pointing this way, the other one is pointing that way. In other words, the two faces are on the top of each other. So look, if I say do it and okay that, first of all, nothing happened, right? They are not on the top of each other yet, but remember I told you, whenever you apply something and you want it to be effective, you have to update. Now they are on the top of each other. And that is exactly what we want, isn't it? Because now if I move this guy along the y-axis, this is the kind of thing that I wanted, right? Now if you say the same, what happens? Then that's not what you want. Look, I double click, go back here, and say change it to same. Look what happens. Yeah. Now they are penetrating each other, and that's not what you want. So whenever you put two faces together, make sure that the normal vectors to them are in the opposite direction, not the same direction, okay? That's an important thing. So far, I could put the faces on the top of each other. Now, I want to make sure that this hole and that hole are concentric. Now in CATIA, there is no concentric constraint here among this list of constraints, like SolidWorks does. SolidWorks has a concentric, CATIA does not. So if you want two holes to be concentric, what would you do? You make the axes of the holes coincidence. If you make the axes, the symmetry axes of the holes coincident, it means those holes are concentric. So you click on coincidence again and then move your mouse over the hole. When you do, then it shows the axis of it. You choose it, and you move over here. It shows the axis of one. You choose it, and now if you apply update, there we go. Yeah. So now they are concentric, and now if you say, hey, I want to move this in the Y, you cannot, of course. Say I want to rotate it about x-axis. There we go. That's the type of motion that you wanted. And then you can also bring in the output member and do the same thing. So the output member here is the blue. By the way, you can rename them if you want to, right? So you can right click here, go to properties, and let's see if we can change the name of this guy. So this guy here, I change it to output. This guy here, I change it to, that's the red member, so it is the connecting, or I can call it Conrad. Then I have this guy, I can change it to input. So feel free to change these names to be something more meaningful than part 1, part 2, or something like that. I always suggest you do that. There we go. Now they are a lot more meaningful. And by the way, before something crashes or so, make sure you save it. So I would save this guy and save it as 4-bar linkage. And it is going to be an assembly, and assemblies are dot cat product. Good. So now let's do the same thing for the output link. So the output link, we make sure that, again, this face and let's say this one are coincident, and then we want this whole axis and this whole axis to be coincident too. So now you can rotate this member as well. And finally, we do the red member with both of them. Of course, one of them is enough, we'll see, for the coincidence of the faces. So I say I want this face and this one to be coincident. Now I have a question for you. Do I need to apply the coincident also between the yellow member and the red member too for the faces? And the answer is no. Why? Because the thickness of the yellow and the blue are the same. They're all 0.1. Every member is 0.1 in thickness. And the yellow and blue, they both have coincident with the green. So this face and this face are already coincident. Now when I say this back face of red is coincident with blue, since these two guys are coincident, it means it is already going to be coincident with what? With yellow as well. I can see it from the top view. So the important thing is, do not, you see clearly, do not over constrain your assembly. It is not going to end up well. It is going to give you errors. So never over constrain. Just like in Sketch, you never over define. In assembly, never over constrain. But you need to make sure the holes are concentric. So you click on this, you go there, and then you come here, and rotate it a little bit to see it better, like that. And then you would do a similar thing for this one, and then this one. Okay, so now we can try rotating about x-axis one of these members. There we go. So now the length of these members is such that the yellow member, the input, rotates all the time fully, while the blue member only goes a little bit back and forth. So this kind of 4-bar linkage mechanism, there is a name to it, and we call it crank rocker. So the yellow member is the crank that rotates all the time, and the blue that only goes back and forth, we call it rocker. Okay, so if you want, we can save it as crank _ rocker 4-bar linkage. Okay, this is more meaningful. Okay, now that we made the assembly, let's learn about some more advanced stuff. So that was quite easy. And the only two constraints that so far we have used is coincidence and fix, but we have the angle constraint. So we can put two faces at a fixed angle with respect to each other. We can have offset constraint. So we put two faces at a fixed distance from each other, flat faces. And then we can provide a contact between the members. So when we say contact, they can slide in one direction, but in the other direction, normal to the faces, they cannot move. Okay, you can fix two members together at the current configuration, and so on and so forth. And then we can convert a rigid assembly, subassembly to flexible, and so on. We'll talk about those. But one thing I wanted to talk about is you made the assembly, and now you find out that, well, I need to modify one of these members. Maybe I want to make, let's say, the blue member a little shorter or taller or something like that. How do I do it? Do I need to close this, go back, open that blue member, edit it, save it, come back, and when you do that and come back to assembly, then assembly will ask you, hey, one of the components has changed. Do you want me to update the assembly? And you say yes, and then it happens and everybody's happy, life goes on. Do you want to do that? You can, but there is a faster and more efficient way. So instead of closing this, opening the part, saving, changing, saving, coming back, and then updating the assembly, what you can do is directly from here, go to that part and modify it and come back without closing the assembly or opening that really. So here, this member is this output, and what I do, look, I expand it until I see the parts body, and then I double click on the part body. And guess what? Look at the environment now. It went from assembly workbench to now what? Part design workbench. Now I am in part design. And now in the part design, I can go ahead and double click on the sketch, and I can change this. Maybe I don't want it at 120, maybe I want it at 110. Okay, and I get out. Clearly you see that constraint is violated because I made it shorter, but no worries. Once I go back to assembly, I can get everything updated. So I made this shorter, good, but I'm still in what? In part design. How do I go back to assembly? Never do the mistake of going to start mechanical design assembly. Never do that. What you need is double click here on the product to go back to assembly. Just like that. First, do an update so that the concentric thing is applied again. Then do a save. When you do a save, not only the assembly is saved, also that part that you made shorter is saved as well. Okay, so just that simple, I could modify a component from within assembly, right? Just expand it until you see the gear part body, double click on it, go to part design, modify, then double click on the product and go back to assembly and save everything, just like that. So one thing was modifying an existing component. Two is, what if I want to now add some pins that go inside these holes and make it more realistic, right? In real life, they are connected by pins, right? So let's make a pin. You know, the thickness of the pin has to be what? 20 units, because each one of them is 10 units thick. And then the diameter of that should also be 10. And I need 4 of that, right? So what do I do? Again, do you create a new file, a part, create that small cylinder, the pin, save it, then come back here and then go to existing component and bring it? Sure, you can do that. Or can you start creating the part without going to a new file or anything right from here? Can you insert a new component and start creating it while you are not even leaving the assembly? Yes, you can do that, and actually this is way more efficient, and I'll show you why. So first thing, add a new member. How do I add a new component? So I go to insert, right? And I say I do want either a new component or a new product. What's the difference? New product is a subassembly. New component is just a component. So click on this guy. And now you expect another part like that to appear on the tree, but nothing happened yet until you click on this product. When you do, now something has come up here. But you see here is called product, which is quite interesting. Let me see. Oh, I should click on new part, not new component. Okay, let me delete this. You need to insert a new part and then click on this. There we go. And then now this guy, you can rename it if you want. So here it's called part 1. I can call it pin. And then this pin is empty. Okay, if I expand it, the gear part is empty. Of course, you haven't done anything. But now I can double click on part body and go to part design. You see I'm in part design. And then I select the front plane. And then I can create what? A pivot, a pin, I'm sorry, with 10 units diameter, and then go ahead and extrude. But now, what was the advantage? I said there is an advantage to doing this. What is the advantage? So sometimes you might not even remember how much was the diameter of these guys, right? Because you want this to be the same diameter as those. So how do you do it? In that case, what you want to do is you can either measure them if you want using this measure tool, right? So it will tell you that the radius was 5. Or what you can do is you can go ahead and draw your member here. Look. You can draw your circle here at this center and with the same radius. How can I do that? Well, I make this, then I choose this guy and this one, so I can refer to the entities of the assembly in this sketch. That's the advantage. And then say, hey, I want these two to be equal. Yeah? Now you're forcing them to be equal without even knowing how much was the radius of that hole. And now you get out of there, and then you do it. And there we go. And I guess gray should be a good color for itself. And then you double click back on the product. Right? So there we go. I got my pin. Now first do a save before anything else. And now the question is, I created a part called pin. Is there really an external CAD file called pin in the same folder that I made the rest of them? Well, let's go look. So if you go and you see, yes, there is. So CATIA actually added a separate CAD file called pin for you in the same folder, okay? Now, I got one pin, I need 3 more. So what do? I can click on this existing component and click on the pin 3 times and bring it 3 times more, and I get my 4 pins. Or I can probably do a copy and paste here. A better way to do it is called multi-instantiation, okay, which I added here. So in Multi-Instantiation Tool, this guy, we can create as many replicas as we want from a component that we brought in without need to go on the existing component and bring in it several times. Okay, this guy here creates one replica, the other one creates in a pattern. So let me show you these two guys here, these two tools that I have over here. So this is actually not, that one is here, and this guy, they look quite similar but could be misleading. So if you expand it, this one will give you one replicate. So all you need is, with this one selected, you click on that, and there we go, that's another one. If you want, again, you can click on one of these, you can click on that and get another one, and so on and so forth, right? So each time you click on this with the component selected, it gives you one more. Or if you want several at the same time, you choose this guy and say I want to instantiate this one, and it says how many. I say I want 3 more, and it says, okay, in which direction, along which axis do you want them to be repeated? It doesn't really matter, but you can choose. Say I want them maybe along the y-axis with so many spacing, and there we go, this is 3 more, and you're good. Okay, so I recommend you use the Multi-Instantiation Tool. That is a very good tool for fast creation of additional members. And now what you need to do is you go ahead and you select this axis with this one to be coincident, and then you select this front face to be coincident with this one in the same direction. There we go. Then you keep doing the rest, so here and here, and then this one and this one, then you repeat here and here, and here and here, and finally here, and can get this guy. I don't think I can. That's okay. Oh yes, I did. So this one and this one. There we go. Right? Perfect thing. It's working all fine. And now it's a lot more realistic. And if this plane's bothering you, you can hide them. Okay? If there are too many of these guys that you don't like, you can go ahead and hide them so that they are not interfering with what you see. But now I guess my assembly is a lot better. So we learn about the important thing that we can edit an existing component, we can create a new one right in assembly and use the rest of the assembly as a guide, and we can use multi-instantiation to create fast replicas of a component that we brought in. Okay? So we talked about that. Now, as I said, you can bring a sub-assembly. So sometimes your assembly is too big that it has sub-assemblies, right? So let's say if we go back to that picture, let's say you want to do the person and the bicycle, or let's say you want to do this guy here or this one here. So it has more than one subsection, right? So what you need to do is bring each subsection, which we call a sub-assembly, bring them separately in, and then put all of those sub-assemblies together, right? For example, let's say in this case, you bring in this 4-bar linkage, and then maybe this guy has some separate subassemblies and so on and so forth. So when you have a big machine or big structure, sometimes you have sub-assemblies. And in order to bring a sub-assembly, you can go under insert and say what? Bring a new product. So you click on it and then you click on product, and there we go. You see, that's the difference between a product and a simple part. So this is an assembly of its own. And if it has components under it, then you can expand it. Right now it is empty, but if you want, you can double click on this guy and you can bring some component for that. Maybe this is a Higgs bolt, something. Of course it's not, but you see now this is a sub-assembly which belongs to the big assembly, right? Yeah, so that is one thing that I wanted you to know about it. Bring in a sub-assembly, and the other thing is when you bring a sub-assembly, there are two versions of a sub-assembly you can add. One is called the rigid sub-assembly, the other one is called flexible. What's the difference between them? First of all, icon-wise, a sub-assembly that is rigid, the two gears that it has, one of them is yellow, one of them is blue. A flexible sub-assembly, one of them is yellow, one of them is purple. So you see, this one that I just added over here and I deleted it, this guy, look, new product, and I clicked here. If you see, it's yellow and blue. So this guy is a rigid sub-assembly. Now, I can convert it to flexible one, but first, what's the difference between these two? So in rigid sub-assembly, what you have is, if you have basically so in rigid subassembly, if you have some components, right, and these components are constrained in a specific way together, and let's say you need two of this subassembly in the major product. So for example here, I basically need to, this product 3, I need another copy of this product 3 added to this product, right? So I need to basically have two instances of this subassembly called product 3 inside the major assembly. Now, we know that they are the replica of each other, and each one has some components in it which are constrained in a specific way. Now, if I go inside this first replica or first instance and I change something in the constraint or something in the components of it, when I get out and come back to the major assembly, I see that the same change that I applied to instance number 1 of the subassembly has been applied to the components in the second instance of the subassembly. Why? Because they are copy and paste and they depend on each other, right? Because the first one is like the major, the second one is like a copy of it. So if I change one, the other one would change automatically. It's like when you projected the sketch, remember in the Sketcher workbench, when you projected the sketch on a plane and you didn't isolate it, if you change the original sketch, the new one would change accordingly. That's the same thing here, right? This one is like the projected version or copy of the first one. So if I change the first one, the second one would change as well. But sometimes you don't want that. Sometimes you have two instances of the same subassembly, but you want to apply a change in only one of them, and you don't want that to affect the other one. So what basically you want to do is to isolate this same subassembly, the instances of the same subassembly from each other. You want to isolate them. How can you do that? If it's rigid, you cannot do it, as I said. When they are rigid, the change of one will affect the other one. When they are flexible, you can do that. So setting a subassembly flexible means it is isolated from the other instances. And in order to do that, what you need is you click on this guy, says, so you select this, and then you click on this command here under Constrain, this one, which convert the flexible to what? To flexible one, right? So you can select this and then do it. So you see here that I tried to do it and it gave me error. Why? It says the object is not valid. Why is that? So you can only do it when the subassemblies are not empty. When I did it, there was no component inside each. So now what I did was I added this hex bolt to both, so now they are not empty, okay? So you need to make sure your subassemblies are not empty. If you are empty, you cannot make them flexible. But now that they are not empty, I can select this guy and then click on this. And look now. You see, it is purple and it means this is flexible. So if I go inside this and do something, change something, it is not going to affect the blue one because this guy is flexible. Okay, so that is really important. Okay, so one of the other things that I want you to know is sometimes the assembly might have a clash, which means you assembled it, but if you run it full motion, okay, let's say in the case of this 4-bar linkage, if you rotate the input member full rotation 360, then somewhere in between, maybe here, if you didn't assemble it properly, the conrod would hit the ground member, okay? And CATIA automatically does not consider that and keeps going. So it does not say, hey, there is a clash, the objects are penetrating each other, let's stop it. You cannot physically do that. No, but it gives you an option if you want to stop the manipulation at the clash. So let me show you that. So here, we don't really have much of a clash, right? By the way, if you want to analyze whether there is a clash or not, in this case, you can do clash analysis, and the toolbar for clash analysis is down here. It's called space analysis, and that is this first one. So if you click on it, and then it says, okay, what do you want to analyze? You say contact plus clash, clash only, whatever. And then do you want it between all components or just between two components and so let's say I want it between all components. Okay, is that going to happen? Or let's say between two components and I want the component, one of them to be this member and the other one to be this member. Is the conrod and the ground going to hit each other as this guy goes through one full revolution? And if you do that, then you see here it shows this window and says, well, no, nothing happens. And then you see this green light says, well, I don't detect any contact, any clearance, any clash, anything. So you are safe. This is going to work in real life. Now, as I said, and you know that this guy is actually going to work without any problem, right? You see no penetration of any kind. Now, if on the other hand, you the way that you did this red member with the blue member, you did a coincidence. If you change the planes involved, which was, let me find it for you. So these are the pins. This guy here. This was between the back face of the red member and the front face of the blue member. Okay, so let me change it and bring the front face of the red member coincident with the back face of the blue member. In other words, make the red member with the green member coplanar. Put them both on the same plane. See what happens. So here, I'm gonna delete this, or I can modify it if I want to. So let me just delete it, doesn't matter, and say now, instead of that, I want this one to be coincident with this face. Okay, and then I need to also modify those pins. So let me modify the pins. So this is this pin here, which has a coincident, right? So this guy, if you look at the pin, you can find what is what. So another way that you can do it is if you want. So I need to right now find out which constraint was the fact that I said the front face of the pin is coincident with the front face of the red member. Okay, I need to find that and modify it, right? So I need to look around and find it, which maybe is this one. But you have to find out, okay? So here, if you double click on it, it might tell you which, so you see the pin and the conrod were involved, right? You see, pin and conrod, so that is the right thing. Now, you might, instead of conrod face, say, well, no, I don't want this, I want to change it, right? So actually, it's this guy here, and I can delete that, and I say, well, actually, I want the front of the input member to be coincident with the front of the pin. So let me just modify it. Right, and then you need to do the same thing here. So you need to first find it. And if you see, in front of each constraint, it says the constraint is between which two parts. Another way to realize this, if you go under Analyze, and then go to this guy says Dependencies. If you click on that and then double click on this product, it shows you each one of the constraints, and then when you double click on each one, it shows you it is between which two members. Okay, so you see here, this says between part 1,6, which is one of the pins. Let me move it to this side so that you can see better. So it's between this guy here, pin 1,6, and then what? This one. So that is the other one that is wrong, right? So you can also see them with more detail here if you want under analyzing assembly dependencies. So yes, it is this coincidence number 12 that has to be changed. So I can go ahead and delete and replace this one and say, well, actually I want the front face of that and the front face of this pin to be coincident. There we go. So now I got it under control. That's exactly what I want. Now let's see. If I do a manipulation here, what happens? Look at here. You see here, the red member and the green member are physically penetrating, which cannot happen. So what you do instead is there is a check from which you can stop the manipulation at the clash, right? And I mentioned that for you here, that the icon, the command to click on is this guy, which you see a star, which is clash. So let's first find that. That's this bottom one here in this toolbar. So you click on that, you turn it on. Now, if I do manipulation and try to move the X member, look, hit, stop. You cannot go any further. Go back, hit, stop, right? So it gives you the dead angles, the angles beyond which you cannot move, right? So I recommend, in order to really make your assembly as realistic as possible, when you want to manipulate it, always turn this guy on, so that if there is any real physical clash happening, this one would stop it, right? So this is very important. Or maybe somebody asks you this question: hey, what are the angles that this rocker member, the output member, is oscillating between? So if this member is oscillating between two angles, one of them being this, the other one being that, right? What are these two angles? So what is this angle between blue and green, and what is this angle between blue and green? So let's say this is one of the end angles. How do I measure that? So I OK it, I put it in this dead position, and then I see it from the front view, and now what I need to measure is the angle between this edge and this edge, right? So I bring my measure tool. See, okay, I don't see it here. Let's do a restore position. There we go. Now I bring this guy and say I want the angle between this one and this one. So you see right now it is not really giving me the angle between these two, right? If I do this and say between any two geometries, now I click on this one and this one. Let's see. There we go. Now I can see the angle, 73.21. That's the max angle that the rocker member can have. And then if I go under manipulation and turn this, this is the main angle, and again I can measure that, right? So I can say what is now the angle between them, and you see it's 17 degrees. So it's between 17 and 70 something degrees. That's what the rocker can go back and forth. Okay, so this is a very useful command: stop at clash or collision. Okay, so I talked about that one. I talked about detecting a clash itself. I also talked about dependencies, I assume. Now, a few other things. One is I showed you how to bring a new member and create it. I showed you how to modify an existing member. Now, one other thing you can do in assembly is to replace an existing member. So sometimes you might say, well, in this here, I found that I would rather actually have two red members here with the size of the red member. So I want to replace the yellow member with the red member, which is a little longer. Can I replace this member with that? Yes, you can if you want to. First, let me see if I can get those pivots back. Or the better thing I do is, instead of some Control-Z's, since I didn't save, I would rather go and reopen this thing. By the way, the last stuff that you opened can be found right here. Okay, so this is the one without the clash, and that's what I like. And as I said, let's say I want to replace this input with another conrod. So how do I do that? Again, if you go back to this product manager toolbar, so you see here, these are for inserting component, product, part, existing component, and so on. This is the one I'm talking about, the middle command. It's called replace component. So you click on this, say I want to replace input. So you click on input, and then it says fine. Now find me the replacing component and say I want the conrod to replace that. Then it says, okay, that yellow member was involved in 5 constraints. Do you want this new member to take over those constraints or inherit them? Or no, you want them to be deactivated and you go and redo those manually yourself, right? So here, CATIA is going to do its best to replace the yellow member with the red member in 5 of these constraints where the yellow member was involved. So the red member inherits those constraints from the yellow. and completely replace it. Or you might say, no, I'll do it myself. So let's see what CATIA does. So if you do it, right, which you did here, and if you update, right, so that everything takes effect, now let's see if it does what we wanted it to do. And you see it does. Now, it's quite interesting. If you look in this case, as I told you, depending on the length of these members, this mechanism would show different behavior. So right now, if you see, in the previous case, when I used the shorter input link, the input link could go full revolution while the output only does the rocker. Now here that I made the input link longer, even the input link cannot go full revolution. It locks itself. Look, here the mechanism cannot go any further physically. And here too, locks. So this is called rocker-rocker. Both of the input and output can only go from certain angle to certain angle. And there is a case where the length of members in front of each other, opposite each other, is the same. So the ground and the conrod are the same length, and input and output are the same length, and that is when you have a parallelogram, and in that case both input and output do full revolution. It's called rocker-rocker, and the RPM of the input and output are the same, and that is what you use in trains, okay, because you want the front wheel and the back wheel and the rest of them all to rotate at the same RPM and move with the same velocity. One of the other things you can do is you can find the degree of freedom for each one of these members in the assembly. So if you go under Analyze, Constraints, then for degrees of freedom, it shows each one of these members have like 1 or 2 degrees of freedom here. So the original 4 members, they all have 1 degree of freedom. And the pins, 2 of the pins, the bottom pins, they have 1 degree of freedom, but these 2 guys at the top, they have 2 because they can move along X and Y, and this member is not even included because this has basically 0 degrees of freedom. Okay, so this is to find out the degree of freedom for each member. A few other things that you want to know. One is the exploded view. This is what you would use for basically creating instruction manuals and installations and showing which components does your entire assembly have and how to put them together. So like this case here, a coffee brewer. So this is the entire assembly, and then this is the whole machine basically exploded and taken apart. Okay, so this is always useful to show what components are involved in your machine. So I'll show you over there here. If you go to this move toolbar, the third command from the top or second from the bottom is called exploded. And if you go here, then you can apply it. Then it's gonna explode it for you. And now if you take this slider back and forth, you can put it back to being assembled. Or you can do the exploded view and basically unassemble it, right? Disassemble it. So this is what you have. Okay, now if you, instead of cancel, you say okay, it says, hey, now you really disassembled it. Now, what would you do? It's like basically you ruined all of those constraints that you applied, right? So now it's not a mechanism anymore. It's just a bunch of disjoint members. What would you do now? You might say, oh, do I need to go and apply all of those constraints again? No, actually, you see, they're all there. All they need is what? An update. So you just update it, it goes back. As long as they exist, once one of them is violated for any reason, either you manipulated without respect to constraint or you exploded or something, just click on update and they will all go back effective. Okay, so don't worry. Now, assembly features is a quite interesting thing. So sometimes you can apply some of the things that you did in part design, you can apply it to the entire assembly or some members of the assembly. Okay, so that is quite interesting. Let's say, for example, here, you find out that I want to do a cut in the yellow member and the green member both at the same time. I need to cut a portion of both of these members for some reason, let's say to avoid a clash or something, although here you don't have a clash. But you want to apply something like a cut extrude to several members. How would you do that? Okay, that is called assembly feature, and this is this toolbar here, the first command. And these are the type of things that you can do. So you cannot do everything you did in part design, just some, like a split. That's what we're going to do later when we do surface design and generative shape design. I'll show you how to use a split. We can do a whole command, can do some Boolean operations or pocket. Let me do a pocket. So in order to do a pocket, you need a sketch. And in order to create a sketch, you basically need an initial plane, right? So the first thing you need is an initial plane. And let's say if I just go here and click on this plane, and then double click on this plane, and then go to sketch, and then draw something. Let me turn this off. Let's say I want to cut this area out. Double click, go back to product. So now I have this sketch. Can I use that to cut my assembly? So look, if I say I want to use that sketch and do a pocket, it says, okay, some members could be affected. Which one do you want to be affected? Whatever you want to be affected, bring them down. If you don't choose any, then it's not going to do anything. So let's say I want to cut what? The yellow member, which is the input. So I bring it down. And I make this true last, right? And if you see here, although it could have cut the green member too, but because I didn't select it, it only cut what? The yellow member, right? Maybe too many of these planes are on the way to see this better. Let me hide them. We have too many planes. Let me get rid of some of them so that you can see a little better and I can see better. There we go. Okay, so here you see that member is cut by this sketch. Now, if I double click on this and say, well, I also want the ground member too, the green member, to be affected. Now look, here we go. Now both of them are cut by that circular sketch. Okay, so this is called a an assembly feature. And as I said, only these 5 commands can be applied to all or a few members of the assembly. Okay, so that is an interesting thing by itself. Instead of going in each one of them separately and cut them, you can do one sketch and then apply it to the whole assembly. What else? One of the other things I want you to know is called bill of material. And bill of material basically shows which parts are included in the assembly, how many of them do you have. So it's like a list of components. And this is another thing like those that you see in instruction manuals, right? Which says this part that you want to assemble has 10 bolts, let's say 1 Allen wrench, and then let's say 2 panels, and then so many legs and so many things on. So this is basically what the bill of material is, okay? you can, if you want, later I'll show you, you can add the material of them. So it's not really the way that you see it right now. It's not bill of material, it's like bill of components. But if you want, you can also provide descriptions and material for them also under these tables. Now the thing is, the file that CATIA exports the bill of material to is a text file, or HTML file, or XLS file. So you can choose which format you want. Okay, so here I have 4 members and 4 pins, right? That's what I have. And if I go under Analyze and say I want a BOM, or bill of material, it says okay. So these are your members, right? And these are their hidden properties. If you want those properties to be shown, bring them to the left. Like, for example, the name of it, type of it, part number, revision, product description. If you want, you can bring it here. Then like what? Nomenclature, whatever you want to be shown, you bring it to the left side, right? So on the right side, you don't really, if any of those are on the right side, it's not going to show on the table. So product description, we want it, so we add it. And then you say save as, and here you can choose whether you want an HTML, text, or Excel file. Let's for the moment say text file. And I save it as BOM of 4-bar linkage, right? And I OK that. Now if I go there, I should be having a text file like that, right? Where you can see here, basically, you have so many quantities of these parts, right? And if you want, I can add revision, nomenclature, and so on and so forth. So this is the kind of bill of material that you would get. Okay. Now I just saw one more thing that I want you to know, and that is I just saw it is reframe on. So let me show you that as well. So when you have an assembly, I just want to know where to add a slide for it, but let me show you first. So if you have a big assembly and there are too many components, and sometimes you might not even exactly know, of course if you click on them you might see them, but sometimes if there are too many components around them and they are occluded by other components, so if there is a big component in front of this yellow member, even when I click on it I don't see it, okay, because it's seen by something, it's occluded by something else. So one of the things I can do is right click on this, and then this is the one of the contextual menu items we did not talk about so far, reframe on. So it's going to focus on that component. Look, it only shows that, right? Or if I want to reframe on the output member, I right click and say, hey, no, reframe, zoom on that member. And it shows that, right? Or let's say I want this pin here, this guy, right? And I say, no, reframe on that pin. So this reframing on something actually is a good way to just focus on the component that you are interested, you want to modify it, you want to see its behavior,